Okay, to start today's lesson, let's just talk about some concepts. So we've been looking at systems of equations, and if you have a system of two equations and two unknowns, for example, let's say we have the equation 2x plus 3y equals 6, and maybe x minus y equals 10. Well, we know that those represent lines, so let's just make up a sketch here. It's not necessarily going to match those two equations, but we know we have one line from one equation and another line from another equation. And if those two lines intersect, then the point of intersection is the solution of the system. So what we're going to do today is expand this idea to three equations and three unknowns. So if you have a linear equation in three variables, it's not a line, it's a plane. So we can see some pictures here. We have a red plane, a blue plane, a green plane. Think of a plane as a surface, like a piece of paper, a wall, the floor, something like that. So a linear equation in three variables, when you graph it, you get a plane in three dimensions. And the graphs of three such equations that form a system are going to be three planes. Now, will the three planes intersect? It's possible that all three planes intersect in exactly one point, as we see here in the first picture, and so there would be exactly one solution. It's also possible that all three planes intersect in a line, in which case you would have infinitely many solutions, all the points along the line, or if they're actually all the same plane, then you would also have infinitely many solutions. Now, there are some situations where you could have three planes and there is no solution because there's no common point of intersection. So let's take a look at this picture here where some of the planes intersect but all three planes don't intersect, so there's no solution there. And the same thing happens in the second picture. We have some intersection points, but we have no intersection points of all three planes at once. And then here we have no intersection points at all, so there would be no solution to any of those systems. Okay, now what will it look like algebraically if you have a linear equation in three variables? Suppose we use the variables x, y, and z. We don't have to, but that's common. Then you'll have an equation like this: ax plus by plus cz equals d, where a, b, and c are not all 0. Now, maybe one or two of them are 0, but they're not all 0. And so if you had a system of three linear equations, you would have three equations, three unknowns. And the solution would not be an ordered pair, but an ordered triple. And typically we'll put those in order alphabetically, x, y, z. And that would be the point that makes all the equations true. So let's get into the algebra of how to find those solutions. So let's figure out what notes number this is today. Okay, if I figured it out right, this should be notes number 11. I hope I got that right. I hope you would let me know if I get off on my numbers. So, in your book you'll notice that there are different methods for solving a system of three equations, three unknowns. There's substitution, which I'm not actually doing. There's elimination, and that's the method I'm going to focus on. And, well, graphing is just not practical to do by hand, and you could do that on some kind of a computer system. But we're going to focus on the elimination method. And as you can imagine, the process is going to get complicated, so we need to be very organized and keep track of what we're doing. So I like to start by labeling my equations 1, 2, and 3. And then I like to indicate which equations I'm working with as I go. So what I want to do is take two of these equations and eliminate a variable. And there is not just one right way to do it. You could do it any number of ways. So that's another reason to keep track of what you're doing, because if you do it one way and someone else does it another way, you have to be able to figure out and follow your own path. So I'm looking at this. I think I'm going to try to eliminate y. So I'm going to take equation 1 and multiply it by -2. And that gives me -4x plus 2y minus 12z equals 8. And then I'm going to take equation 3 as it is. So notice I'm labeling the equations I'm using. Number 3 as it is, -4x minus 2y plus 5z equals 9. And then if we add these equations together, we'll cancel or eliminate the y terms. So we have -8x minus 7z equals 17. And I'm going to call that equation 4. So now I have an equation with two variables, x and z. What I would like to have is a second equation with the same two variables, x and z. So I'm going back to my original three equations and I'm going to choose a different combination and eliminate y again. So let's say I take equation 2 and equation 3. And let's say I leave equation 2 as it is. And let's say with equation 3, I multiply it by 2. And then if we add these equations together, the y terms will be eliminated. And we have negative 2x plus 5z equals 11. And that will be equation 5. Okay, so at this point, we're going to take equations 4 and 5 and try to eliminate something, either x or z. And I think I'm going to try to eliminate x. So I'm going to leave equation 4 as it is. And it is so easy to make just a very small error on this, just a calculation error or something, or drop it negative and mess up. So be sure to really keep your work organized. So I'm going to take equation 5 and multiply it by negative 4, and that gives me 8x minus 20z equals negative 44. And then if I add these equations together, the x terms are eliminated, and that gives us negative 27z equals negative 27. Well, that feels really good. Divide by negative 27, we get z equals 1. We know we shouldn't always expect the answers to work out to such nice, simple numbers. Sometimes they're fractions, sometimes they're not pretty, but it sure does feel good when they turn out. Okay, so now that we know z, let's work backwards and find x and then find y. So I'm going to use either equation 4 or 5. It really doesn't matter. I'll take 5 and substitute 1 in for z, and that will allow me to solve for x. So negative 2x equals 6, so x equals negative 3. Now I'm going to go back to equation 1, 2, or 3, it doesn't matter which, and substitute the values of x and z in there and find y. So suppose I take equation 1, so 2 times x minus y plus 6 times z equals negative 4. So negative 6 minus y plus 6 equals negative 4. So the opposite of y equals negative 4, y equals 4. Now, we write our answer as an ordered triple, x, y, z, negative 3, 4, 1. And we should double check by just taking that ordered triple and substituting it into equations 2 and 3. Since we already used equation 1 here, we know it works, but substitute those into equations 2 and 3 as a way to check. I'm going to leave that for now because I know we have a lot to do. So continuing with today's video, let's try number 2. We're going to go through the same process using elimination. Here's equation 1, 2, and 3. And let's choose a variable to eliminate. And what you choose and what I choose might be different. I think this time, well, looking at it, you just want to stop and look for a minute. I think eliminating y kind of makes sense if we look at those y terms. So I'm going to start with equations 1 and 2 and leave them both alone and add them together, and the y terms are eliminated. So we have 3x plus 3z equals 9. And that's equation 4. And then we need to eliminate y again. So perhaps I use equations 2 and 3. So I'll leave equation 2 alone. And equation 3 I'm going to multiply by 3. And then we're going to add those together to eliminate y. And we have 9x plus 9z equals 29. Okay, and that's equation 5. So, we're going to use equations 4 and 5. So suppose I decide to multiply equation 4 by 3. That gives me 9x plus 9z equals 27, and equation 5, if I leave it as it is, 9x plus 9z equals 29, and this time I'm subtracting. Remember, you can subtract, you don't have to add the equations. 9x minus 9x is 0, 9z minus 9z is 0, so we have 0 on the left. 27 minus 29 is negative 2. 0 equals negative 2. Well, that's not true, so what does that tell us? Remember what it told us for a 2x2 system? It's the same idea. We have no solution. We come up with a contradiction, we have no solution. Now why? Is it because the three are parallel, or is it because only two of them intersect and the other one doesn't? We don't necessarily have that information. We could probably think about it a little further if we wanted to kind of get down to that, but all we really have to do for the sake of this problem is say no solution. Okay, here's number 3. Let's do the same thing. In fact, if you want to pause the video and work it out and then resume and see how you did, I'm going to go ahead and, I'm going to do something kind of slick here. I'm going to eliminate two variables at once. I'm going to take equation 1 and equation 2 and subtract them. You could also multiply one of them by a negative and add them if you don't trust yourself with subtracting and getting all the signs right. So x minus x is eliminated, y minus negative y gives us 2y, z minus z is eliminated, 6 minus 6 is 0. Okay, it's all right to have 0 over there, and it's all right to divide 0 by 2 and get 0. 0 is still a number. So that doesn't mean you have a contradiction, that just means you have the number 0. Okay, so now let's go through and see if we can find the values of x and z. So if we substitute 0 into our equations, equation 1 is now x plus z equals 6. Equation 2 is now x plus z equals 6. And equation 3, if I divide it by 4 and substitute 0 in for y, I get x plus z equals 6. X plus z equals 6 is a line. So if you think about this three-dimensional plane, we have an intersection that's a line, and all the points on the line have a y-coordinate of 0. The x and z coordinates can change, but they fall on a line. So we have infinitely many solutions. Okay. Oh, that was fast. I thought there would be more. Ooh, I hope you're not disappointed by a short video today. Well, what you gonna do? Okay, so here's your assignment. I did throw in an even in there, so be sure to ask for the answer next time. Thank you, everybody. Have a wonderful day.